Hello everyone. In this video, we're going to be going over a couple examples on how to find confidence interval for the mean mu when sigma is known. So the first example says, consider a normally distributed data set with a standard deviation of 0.8. Given that a random sample of size 82 from a data set has a sample mean of 31.39, construct a 95% confidence interval for the true mean of the data set and interpret it. So the first things first we're going to do is we're going to write down our given information. So from this problem, we know that we're doing a confidence interval and that we have a standard deviation of 0.8. Now you might wonder, how do we know if sigma is known? And the general rule of thumb is that if it comes from your sample data set, then it's S, but otherwise we treat it as sigma. This would be from a prior study, a manufacturer gave us this information, or if we just give you a statement like this, where we say, consider normally distributed data set with a standard deviation of 0.8. We did not make it in any way, shape, or form sound like it came from our sample data set. So in this case, we have sigma. So we have sigma equals 0.8. We have a sample size of n equals 82. And we have a sample mean, or x bar, of 31.39. Now, generally, with these kind of problems, you are going to be given some confidence level that you want to use to find this confidence interval. Now, in this case, it's 95% confidence interval. So we have a C of 0.95. But if you ever encounter a problem where C is not given, the default for this would be 0.95. So now what we're going to do, before we do any other parts of the problem, is we're going to check our assumptions. So if you remember, our assumptions are, is sigma known? And in this case, yes, we do know sigma because it's part of the problem, right? We're in the part where sigma is known. But we're also going to check our other assumption, which n is equal to 82, which is greater than or equal to 30. So based on both of these assumptions, the fact is, if sigma is known, we can use standard normal z. If n is greater than or equal to 30, we can use standard normal z, or if both are true. So in this case, we are going to be using the z distribution. So use z. Now from there, let's start with our general form of our confidence interval. So our confidence interval is going to be x bar minus e up to x bar plus e. Now, we know what x bar is. This is part of our given information, but we don't know what e is, the maximum margin of error. So there's two ways you can approach this. You can either kind of come outside of this and find your maximum margin of error and then bring it back in your confidence interval, or you can do it within the confidence interval. So I'm going to just do this one by doing it within the confidence interval, and then from now on, after that, I'll just use e from outside. So in this case, if we plug in e, which we know that our e should be equal to, for when the sigma is known, z critical sigma divided by the square root of n. So this is going to be x bar minus z critical sigma over square root of n up to x bar plus z critical sigma divided by square root of n. And we're going to plug in our values and we should be able to get it, no problem. So our x bar value is 31.39 minus z critical. So we need to find this. This is not part of our given information, but the confidence level is. So from there, we should be able to figure out what our z critical value is. We will give you a subtable to the z table, which gives you the critical values, your z criticals, for c equals 0.9, 0.95, and 0.99. But if you didn't have that, the way you would find this is, remember, you need to find the z value where from negative z critical to positive z critical, it accounts for, in this case, 0.95 of the data. So 0.05 has to be the outside. Half of it's down here, which would be 0.025, which means we're looking on the table for where 0.975 is below this positive critical value. So we go to our table, we find 0.975, and we get 1.96. So in this case, our z critical is 1.96. So I'm going to plug that in now. So I get 1.96 times, now I put my sigma in, my sigma is 0.8, divided by the square root of n is 82. And then this is my lower boundary for my confidence interval. Now I need to do the same thing for my upper boundary of the confidence interval, except now I'm going to be adding them. So it's going to be 31.39 plus 1.96 times 0.8 divided by the square root of 82. And this is the reason a lot of times it's actually faster to come out, find your maximum margin of error, and then bring it back in, because that way you don't have to write this 2 times. But either way is perfectly fine. So once we do that, we are going to get that this is equal to 31.39 minus 0.17 up to 31.39 plus 0.17, which is going to be equal to 31.22 up to 31.56. Now, the last part of the problem asks you to interpret the results. So the interpretation of this would just be something along these lines. We are blank % confident the true mean falls between blank and blank. And then you just plug in, right? We had 95% confidence interval, so you'd put that we're 95% confident. The true mean falls between your lower boundary, 31.22, and your upper boundary, 31.56. Now, if this problem had some specific data, like what it represented, you might want to, instead of putting the true mean, you might want to say the average this, or the true mean, whatever it is that you're actually finding, right? The average weight of people is this, the average height of coconut trees is this, something like that. The next example says that a sample of 36 randomly selected candy boxes was recorded with a mean weight of 23 pounds and a standard deviation of 6.7 pounds. Construct a 90% and 95% confidence interval of the true mean weight of these candy boxes and comment about it. So in this case, we actually have 2 problems we're doing at the same time. And this is so that we can kind of compare how your change in your confidence will actually affect your confidence interval. So first thing I'm going to do, I'm still going to write down my given information. So I have a total of n equals 36 boxes of candy. The average weight, the mean weight, x bar, is equal to 23 pounds. Now, notice the way that this is written. A sample of 36 randomly selected candy boxes has a recorded mean weight of 23 pounds and a standard deviation of 6.7 pounds. That means that we got this standard deviation of the weight from our sample because it was our sample is the average weight and the standard deviation, meaning that we have S equals 6.7. So in this case, we are looking at a problem where sigma is not known. Now I'm going to actually split this into 2 parts. We're going to have we have C equals 0.90 and for when C is equal to 0.95. Now, first thing we're going to do before we can do this problem, because we first need to see what sort of distribution we're using, we're going to check our assumptions. So we're going to look at, is sigma known? Well, in our case, sigma is actually unknown because we have S, not sigma. So in this case, that assumption fails. And then we're going to look at our N. N is equal to 36. Well, 36 is greater than or equal to 30. So therefore, because one of these assumptions is true, we can use the Z distribution. So now what we're going to do is we're going to find our confidence interval for both of these confidence levels. So the first one, C equals 0.90. I'm going to start with the general form of my confidence interval, X bar minus E up to X bar plus E. And I'm going to do the same thing for when C equal to 0.95. So my confidence interval is equal to X bar minus E up to X bar plus E. I know what X bar is because that's part of my given information in the problem. So now what I need to do is I need to find what E is. So E is equal to Z critical sigma over square root of N for both of these. Now, you might be asking, why are we using sigma when we just said that sigma is unknown? And what we're doing is we're using the fact that with the central limit theorem, even if we don't know sigma, meaning we don't really know that this comes from a normal distribution, we're saying that if we have normal looking data and we have a large enough sample size, that our S will be approximately equal to sigma. So we're kind of going off of S is roughly equivalent to sigma. So we'll still use the sigma for the formula, even though we're actually using S. And this is because a lot of times in statistics, when we don't have the parameter, we have to use the next best thing, which is our estimate of the parameter. And that's the whole point of a point estimate, is that we're saying that I don't know what the true standard deviation is, but from my sample, I do have a standard deviation, and it's the best value that I have for it. So when we have a confidence level of 0.9, our Z critical is going to be equal to 1.645. When we have a confidence level 0.95, just like the last problem, we will have a Z value of 1.96. And then we just plug in our S, 6.7, divided by the square root of our N, which is 36. So our maximal margin of error for our confidence interval with a confidence level of 0.9 is going to be equal to 1.84. And our maximal margin of error for our confidence level when we have C equals 0.95 is going to be equal to 2.19. So right there, let's do a quick comparison. What happened to our maximal margin of error as our confidence level went up? Well, in this case, we're starting at X bar, and we're going to go out to the left and the right, 1.84. And this is it for confidence level 0.9. For confidence level 0.95, we're starting at our mean X bar, and we're going out 2.19 to the left and the right. So this confidence interval is actually going to be bigger, because if I have some set data, right, my sample, if I want to be more confident that the true mean falls between two values, then I would need to make the interval bigger. So in this case, my confidence interval is going to be equal to, I'm going to plug in X bar, which is going to be 23, minus 1.84, up to 23 plus 1.84, which will be equal to 21.16 up to 24.84. For my confidence interval with a confidence level 0.95, my confidence interval is going to be 23 minus 2.19 up to 23 plus 2.19. And this is going to give me a confidence interval of 20.81 up to 25.19. So notice what happened here is that if I were to draw this normal distribution centered at 23, my first confidence interval was from 21.16 up to 24.84. This is for when I had a 0.9 confidence level. When I have a 0.95 confidence level, my confidence interval has to be bigger because it goes from 20.81 up to 25.19. So notice for this one, my confidence interval had to be bigger to account for that higher level of confidence. In this next example, we have a sample of 20 final exam scores out of 200 for a statistics class are considered for a study. The average score for these 20 students is 150. Based on previous studies, standard deviation of these scores is 15.50. Construct and interpret a 99% confidence interval for the true averages of these final scores. So again, we're going to start by writing down our given information. So in this case, we're looking at 20 scores for the students. So we have n equals 20. And those students have an average score of 150. Next, we need to look at our standard deviation. So notice the way it's written. Based on previous studies, standard deviation of these scores is 15.50. That means that this came from a source outside of this sample, meaning that this is sigma. So sigma is equal to 15.5. And the last thing is we're looking at a confidence interval of C equals 0.99. So now before we move on, we need to check what assumption we're going to use for this problem. So we're going to check our assumptions. So the first one is sigma known. Well, in this case, it is, in fact, known, right? We know what sigma is, so we're good to go there. But let's check our other assumption. We have n equals 20. Now, is this greater than or equal to 30? No. So it fails this assumption. So the fact that one assumption does pass, though, this means that we can use our z distribution. We can use our standard normal for finding this confidence interval. So then we're going to start by writing our general form of our confidence interval, x bar minus e up to x bar plus e. And then here what I'm going to do is I'm going to come outside of this and I'm going to find what my maximal margin of error e is. So e is equal to z critical sigma over square root of n. Z critical for a confidence level of 0.99 is going to be equal to 2.58. My sigma is 15.5. And then divided by the square root of n, which my n is equal to 20. This is going to give me a maximal margin of error of 8.94. So my confidence interval is going to be, plug in your x bar, which is 150, minus your maximal margin of error, which is 8.94, up to 150 plus 8.94. And this is going to give us a confidence interval of 141.06 up to 158.94. And then last step is we need to interpret this. So because we know what this is, I'm going to interpret this in terms of the problem. So we are 99% confident the average test score of students is between 141.06 and 158.94. Or you could say the true mean score of students is between this and this, something like that. But I wanted to put it in terms of the problem. Now, one last thing I want to talk about before we finish up this lesson is what does it actually mean when we're some amount confident that the true mean falls in some interval? Well, whenever we have actual data, right, there exists some true mean. So let's say that our true mean is located right here. Now, this is a value we don't necessarily know, but it exists, right? The average height of all people on Earth exists. The average lifespan of sea turtles exists. We just don't know what it is. So what we're saying is, based on the amount of data we're gathering and everything that goes with it, if we were to create a confidence interval, let's say our first confidence interval would be here. So our mean is within this interval. Now, we don't know where it is in this interval, but we have some level of confidence that it's within this interval. And then let's say we took another sample of the same size and all that kind of stuff. And let's say that this confidence interval was here. So again, the mean falls in there. We do it again, we do it again, we do it again, we do it again. And basically what we're saying is that if we were to repeatedly take this sample, that we expect that some C amount of the time that the true mean would fall in this interval. So if C is equal to 0.95, that's why we're 95% confident that our true mean falls in that interval. Because our mean, our true mean, is not changing. What's changing is our interval. But we're saying based on how big we're making that interval, wherever it ends up being, how often do we expect the true mean to fall in there? Because the real probability that falls in there is either 0 or 1, right? It falls in this one, 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 it doesn't fall in this one, and it does fall in this one. But we don't know what mu is, so we don't know which ones of these are accurate or not. So in this case, what we're saying is that if we were to take this sample, we are, in this case, if C is 0.95, 95% confident that whatever interval we made, that the true mean would fall within it. That means that 5% of the time, we expect that we may be taking a sample that it does not fall within. And this is why it's really kind of important to understand what it means when we make these statements, because we're not saying that it definitely falls within that interval. And we're not even saying that based on whatever our interval is, whether we have the right or the wrong one, because we don't know. All we know is based on the conditions, what's the probability that if we created a confidence interval of this size from this sample, what's the probability that the true mean would be within that interval? Which means that we also know what's the probability that it does not fall in that interval. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.